Hello, my name is Wening Sasanta. My NPM is 2406367615, and I am from Group 17, Batch 3 of Materials Characterization Laboratory. Today, I will present to you guys my work principles of AS, UV vis, STA, and F tier. First, atomic absorption spectroscopy, or AAS. Principle is the absorption of light by free atoms. AAS is primarily used to determine the concentration of metal elements in a sample. It operates on the principle that atoms in their ground state, lowest energy, absorb light at very specific wavelengths characteristic of that element. How AAS works. The image on the right showcases an AAS instrument setup featuring key concept components such as the light source, atomizer, monochromator, detector, crucial for precise elemental analysis in various samples. How its process works is through one, atomization, where the liquid sample is aspirated into a high temperature flame or graphite furnace. This heat breaks the chemical bonds and converts the sample into free atoms or gas of neutral atoms. Two, light source, a hollow cathode lamp or HCl specific to the element being tested. For example, a copper lamp for detecting copper emits light at the exact wavelengths that the element absorbs. Three, absorption, where this light beam passes through the cloud of atoms. If the target element is present, its atoms absorb some of the light. Four, detection. The detector measures the amount of light that passes through without being absorbed. According to the Beer-Lambert law, the amount of light absorbed is directly proportional to the concentration of the element in the sample. Second, ultraviolet visible spectroscopy, or UV-Vis. Its principle is electronic transitions in molecules. UV-Vis spectroscopy measures how a sample absorbs light in the ultraviolet UV and visible regions of the electromagnetic spectrum. It is widely used for quantitative analysis of solutions, for example, determining protein or drug concentration. How UV-Vis works. A UV-Vis spectrophotometer is essential for measuring light absorption in samples, utilizing an integrated light source, sample holder, monochromator, and detector to analyze molecular properties effectively. Taken from the image on the right top, how UV-Vis works is through first electronic excitation. Molecules contain electrons. When UV or visible light hits the molecule, the energy from the photons can excite electrons, causing them to jump from a lower energy orbital or ground state to a higher energy orbital or excited state. Two, chromophores. This absorption happens specifically in parts of the molecule called chromophores, like double bonds or aromatic rings. Three, spectrum. The instrument scans a range of wavelengths. A detector measures the intensity of light passing through the sample versus the light passing through a blank reference. Four, quantification. Like AAS, UV-Vis relies on the Beer-Lambert law, where absorbance is proportional to the concentration and the base length of the sample container, or cuvette. Third, we have simultaneous thermal analysis, also known as STA. Its principle is to measure mass and heat flow that changes simultaneously. STA is a combination of two distinct thermal analysis techniques, which are thermogravimetric analysis, TGA, or DT scanning calorimetry, DSC, or also can be known as differential thermal analysis, DTA. It runs both tests on the same sample simultaneously to eliminate errors caused by varying sample conditions. How STA works is by integrating a furnace and a balance, allowing measurement of thermal properties. It provides crucial insights into material behavior under varying temperature conditions, revealing stability and composition detail. How STA works is one, through heating. A small sample is placed in a cubicle inside a furnace and heated according to a programmed temperature schedule. For example, rising from 25 to 1000 degrees Celsius. Two, TJ component or mass, a highly sensitive balance, continuously weighs the sample. It detects mass loss due to evaporation, decomposition, or oxidation, or also mass gain, which is due to reaction with the atmosphere. Three, DSC or DTA component, also known as heat flow. Sensors under the cubicle measure the temperature difference or heat flow between a sample and a reference. This detects physical transitions, like melting glass or glass transition, that do not involve mass change, as well as chemical reactions, exothermic or endothermic, that do. Four, we get the results, where I would get a single graph showing both the weight change curve and the heat flow curve. allowing me to correlate physical changes like melting with chemical changes like degradation. Both pictures shown on the right are on the top, which is DSC and TGA combining to STA, and the bottom picture shows the inside of STA. Lastly, we have FTR, or Fourier transform infrared spectroscopy. Its principle is molecular vibrations and dipole moment changes. FTR is used to identify organic and inorganic materials by mapping their chemical fingerprint. It measures how molecules absorb infrared radiation. How FTR works. The FTR spectrometer is essential for analyzing molecular vibrations by measuring infrared radiation absorption. Key components include the source, interferometer, sample component, and detector, which work together to produce spectra. Those elements that I said before that includes in the instruments are shown in the picture on the top right. How FTO works is one, to vibrational excitation. Chemical bonds like CH, OH, or C double bond O vibrate at specific frequencies. When infrared light of a matching frequency hits the bond, the molecule absorbs that energy, increasing its vibration, stretching, or bending. Two, interferometry. Unlike older machines that scanned one wavelength at a time, FTR uses a Michelson interferometer. It splits a light beam into two paths and recombines them to create an interference pattern called an interferogram. This allows the instrument to measure all infrared frequencies simultaneously. 3. Fourier transform. The raw data or interferogram is a complex wave pattern. A mathematical algorithm called the Fourier transform converts these wavelengths into a readable spectrum. Intensity vs wave number. 4. Identification. The resulting peaks in a spectrum correspond to specific functional groups. For example, a peak at 1,700 centimeters minus 1 usually indicates a carbonyl C double O bond, allowing for identification of the molecule. Those graphs can be shown top right, nano F tier. Summary of those four techniques. AAS has its cubable atomic absorption of light with primary output of concentration of metals, and it's typically used in case of detecting lead in water, iron in blood. Second, UV-Vis. Its principle is electronic transitions, with output primarily on concentration of analytes, and it's usually typically case of impurity of DNA and drug concentration. Third, STA, with key principle of mass change and heat flow, primary outputting and mass vs temperature and heat vs temperature. Typically used case is to study thermal stability and melting points. Or F-tier. Its key principle is bond vibrations, with output primary in IR spectrum or fingerprint. Typically used case in identifying plastics or drug contaminations. References as below: Ball, Gabbett, Larkin, Mansell, Perkin, Elmers, Cog, and Thomas, with all in APA format reference bibliography. That's all from me. Thank you. Bye-bye.